All right, let's dive in. Today, we're going to talk about a hidden principle that connects, believe it or not, the phone in your hand to the stars in the sky. It's this one fundamental idea that explains why bridges stand strong, how braces can straighten your teeth, and even how we see the universe itself. So let's get right into it.
So, let me start with a question for you. What could a giant skyscraper, a microscopic computer chip, and a black hole out in deep space, what could they possibly have in common? I mean, they're on completely different scales, right? They seem to operate under totally different sets of rules, but it turns out they all share one deep, fundamental secret.
And the answer, it's actually really simple. They all bend. Yeah, that's it. Every single one of them bends. This bending is what scientists and engineers call deflection, and it's the key, the one idea that's going to connect everything we talk about today.
Okay, so let's get down to the basics. What is deflection really? And how in the world can this one simple concept apply to so many wildly different things?
Well, to put it simply, deflection is just what happens when you apply a force, or as engineers would say, a load, to something, and it moves or bends. Just picture a diving board, right? You stand on the end and it curves down. That curve is deflection. It's pretty much the universe's go-to response whenever it gets pushed or pulled.
But here's the thing. Deflection isn't always a problem. Actually, sometimes it's incredibly useful. Take braces, for example. That little wire uses a very controlled, precise bend to apply a constant force that moves your teeth. That's desirable deflection. Now, on the flip side, you have a bridge girder that's bending way too much under the weight of traffic. Well, that could lead to a total collapse. That's the uncontrolled, really dangerous kind that we work very, very hard to prevent.
So let's take a look at how this all plays out in the world we actually live in. On a human scale, managing deflection is pretty much job number one for creating a world that's safe, stable, and, functional. And believe me, this is critical absolutely everywhere you look. Whether we're talking about a bridge that has to stand up to traffic and wind, or a giant wind turbine blade flexing in the air, engineers are constantly, obsessively measuring deflection. It's not just about making sure things don't fall down. It's about safety for sure, but it's also about making things as efficient as possible and knowing exactly when something needs to be fixed. And the precision they need, it's just staggering. I mean, get this. Engineers monitored a massive bridge for 8 months, and they were measuring its movement with an accuracy of 0.08 millimeters. That is literally less than the thickness of a human hair. That's the kind of microscopic detail it takes to keep our gigantic world from falling apart. Think about it. An airplane needs its flaps to deflect at exactly 45 degrees to get enough lift for takeoff. A massive ship's hull is actually designed to flex and bend with the waves so it doesn't just snap in two. Even the panes of glass on a skyscraper are built to bend when the wind pushes on them. In every single one of these cases, it's this constant, super high-stakes balancing act, all about controlling deflection.
But here's where it gets really interesting. See, managing deflection on a huge scale is all about strength and stability, right? But there's this whole other world where we don't fight deflection, we actually use it. We harness it. It stops being about preventing a disaster and starts being about making something work. And to see that in action, we've got to go small, like really, really small.
And that brings us down into the microscopic world. This is where deflection completely changes its job description. It's no longer a risk we have to manage. Instead, it becomes this amazing precision tool that we can use. And that's really the key difference in how we think about it. At the big macro scale, it's all about strength, resisting these massive forces like wind and weight. But down here, at the micro scale, it's all about precision. It's about harnessing these tiny, tiny little bends to do incredibly complicated jobs. Let's circle back to that orthodontic wire for a sec, because it's a perfect example. Here's how it works. First, the wire gets bent, or deflected, when the orthodontist fits it onto the braces. Then, because that wire is elastic, it's always trying to spring back to its original straight shape. That constant trying creates this tiny, steady, and perfectly directed force. And that's what, over time, pushes the teeth into just the right spot. It's deflection used as a perfect functional tool. It's brilliant, really. And this same idea, it's at the core of so much of our modern tech. Tiny little materials are bending inside your phone to help focus the camera lens. We use magnetic fields to deflect carriers inside a semiconductor. We're even using sound waves, ultrasonic fields, to literally bend the path of tiny particles.
It's the science of the small, controlled bend that really powers the world you and I live in today. Okay, so we've gone from massive bridges all the way down to tiny microchips. But the story of deflection, it doesn't stop there. Not even close. To see its final, most mind-blowing form, we have to take the biggest leap of all, from the impossibly small to the infinitely large. We have to look up. And this brings us to the final piece of the puzzle, cosmic deflection. This is where we're not talking about things in the universe bending anymore. We're talking about the very fabric of the universe itself doing the bending. Now, you see a quote like this from a research paper, and it sounds, incredibly dense. It's talking about deflection angle of light and ring-hole geometry. Honestly, it sounds like something straight out of a sci-fi movie. But what is it actually saying? Well, in short, it's describing something that Einstein figured out more than 100 years ago, and it's this. Gravity isn't really a pull, it's a bend. A really, really massive object doesn't just pull things toward it, it actually warps the very fabric of space and time around it. And anything that travels through that warped space, including light itself, has no choice but to follow that curve. And this isn't just some crazy theory, We see it happen. Our very own sun does it. It slightly bends the light coming from distant stars that pass by it. But the effect gets truly extreme when you're dealing with ridiculously dense objects like black holes, or even theoretical things like wormholes or these so-called ring holes. They basically act like giant lenses in space, bending and distorting the light from anything behind them. And this is the ultimate form of deflection. We're not talking about a steel beam bending or a tiny actuator moving. We are talking about the literal fabric of space-time itself being bent out of shape. So when we see starlight curve, it's not because the light decided to take a turn. It's because the actual path, the very universe it's flying through, is curved. So we've taken this incredible journey, right? From the microscopic all the way to the cosmic. Let's try and wrap this all up with one final thought. When you step back and look at it, we've seen this one idea, deflection, show up everywhere. In our biggest buildings, in our tiniest pieces of tech, and out in the deepest reaches of space. From that careful, gentle bend in a wire moving a tooth, to the mind-boggling curve of starlight around a black hole, it seems like bending is just the universe's fundamental answer to force. It's what it does.
So if there's one thing to take away from all this, it's pretty simple. Everything bends, from the smallest things we can imagine to the largest things in existence. So I'll just leave you with this question to chew on. What unseen forces, what subtle little bends and deflections are shaping your world, right here, right now?